In today's video, we will be taking a look at the problem 2.5. So in this problem, we're given this list of letters or a number, and if we're given a list of letters, we have to find which the number that it's in if we sort all of the possible grids in the alphabetical order. And if we're given a number, we're supposed to print out what is the list of letters at that current position. So to do that, we can basically test out if what happens if each of these are assigned a value. So this is quite quick since there are only 25 cells inside this grid, and we will only have 25 letters. But then for this each of these possible combinations that we're looking at, we should use dynamic programming to calculate the total number of possible string combinations if we have our current string set. So I'll show you the example here. So this is our main part of the algorithm. There are two types of operations that we need to do. The first type is if this command is equal to W. If it's equal to W, then that means we're reading in a string and we have to convert that into a number, basically representing which index it's at in the sorted list of all of the possible combinations. And so, as I said, we will loop through each of these indices inside the string, starting from 0 all the way to 24. And then for each of those index, we will set a temporary string to one of the letters that is before the letter inside that current position. So this way we'll be able to check every one of the possible moves before this current string. So when we get the final answer, we should just increase that by 1, which will give us the position of this current string, because the answer will keep track of the count of all the possible moves that are smaller than this current string, since we're looking at the letters that are only smaller than this letter at SI. So we should try each of these letters. We can set our temporary string with this index to this current letter that we're trying out. And then here we will use dynamic programming, and in this function we will use recursion a bit, and just call this count all the possible strings that can be formed if we are given this current string. So at first here I will set the temporary string all to empty spaces. So the empty spaces will represent that any letter can be inside the empty space. And then, so if there are already set letters, then that means we should only have letters that are this CH at that position. So this A will keep track of the column numbers for each of the rows. So this is why I have 6 of them, because I'm using a 1 indexed. So this should go all the way from 1 to 5, which is the 5 rows of this grid. So I'll also use this dynamic programming array. So this will consist of five dimensions. Each of these dimensions will store information about one of these column numbers. So this will represent the first column number, the second, the third, the fourth, and the fifth. So then here we'll at first set this all DP fives to 1. This basically means that at the final grid there's only one. So this is basically if we've traversed all the cells and we're at the final cell, then of course there's only one possible way for that, which is just the current string that we're looking at. Then we will use this count possible moves. So we will look at all the letters inside this alphabet, starting from A to Y, and we will try out every position in this string and see what happens if we count the number of moves that we can get if we set that to this current letter that we're looking at. So I'll name it L here. So every time when we're doing this recursion, we'll first check if these column numbers are already visited. If they're visited, we can just return this DP value. Otherwise, we should find out the DP value, and to do that, we will loop through each of the rows inside this string. And also we have to make sure that the current column number that we're looking at is smaller than the column number for the previous row. This is because this way we would definitely be able to check some of the previous letters first before going down to this current row, which means that we should have filled up the first row first, and then fill up the second row, and then the third, and so on. Because that way we can be able to count the letters inside in the alphabetical order when you're looking at them down the columns and down the rows. So this is why it should be smaller than the previous one always, because we always want to fill out the previous row first before filling out this current row. And then we can check this current position at our temporary string. So basically this gets our row and column number. Since this is the normal column number, and then the row number will be I minus 1 times 5, because this is the number of rows that we're currently looking at, and multiply that by 5 because each of the rows have five letters in them. So we can see what happens. So every time we're given this character L, we check if the letter at that position is equal to a blank space. If it's equal to a blank space, then that means we can try what will happen if we replace this current blank space with this letter L. Another case is if the letter is exactly the L that we're looking at, then that means we can, of course, this is also a case which is possible, so this is also a possible case, and this is also a possible case, so we should try out a number of possible ways for these cases. But now we basically think of this as filling this AI, so basically the column AI at row I. We'll set that to this letter L, and we see what happens next when we're looking at the next column number. So we increase this by 1 first, and then use this count possible moves again, but this time we're not looking at this current letter, we're looking at the next letter. And so here we would increase our total count by the possible moves that we can get if we set this current row and column cell to this L. And then so after we're done calculating this, we should decrease our AI again because we're using it for later uses as well. Now we can set our DP value of these few column numbers to our count, to our total count, because we're given this current column numbers, and we found the possible total possible moves that we can get by replacing the blank space with some other letters. So then finally we can return the count. So this will give us the total count. And so here first I will set all the A to 0 because we're all looking at the first character inside our inside each of the rows. And also I set A0 to 5 because we are not using the 0 index here. So I'm always checking if the current row if the column number for the current row is smaller than the column number for the previous row. So of course we want to make sure that each of the rows have at most a column number of 5. So because like here in the example there should be only 5 columns. So here this will limit all of the all of the column numbers to at most 5. Then as I explained here, we reset the DP value all to 0 and set this all. So if we search up everything, we'll just set this to 1, and then we should add our answer to those total moves that we can get. And this is the case when we set our current temp character to the CH. So we will loop through all of that. So this will, since each of the characters are smaller than our character inside the main string, this will guarantee that it's definitely smaller. The string is definitely smaller than our main string. So the answer will finally represent the total count of letters. I mean the total count of strings that are smaller than this current string. And also every time after we loop through this whole from A all the way to SI minus 1, we should set the temporary the character at the temporary string to the SI as well, because now we're looking at after this current index. So this index should be set to this to make sure that we get all of the possible answers. Then just one case, we just have to print out answer +1 because +1 will give us the position of this current string. And then the other case is the opposite of this, and this is basically the same thing as well, except here we can loop through all of the possible characters and just check if this total number of counts is smaller than this x. So first I will use this t to keep track of the total number of possible moves. And so we'll start at the first letter as well, and we can set that to all the letters from A to Y and see what happens after we do that. So still the same, set the temporary character to the CH, and then reset the A and BP. Then we also use this count possible moves if this temporary letter is set to CH. And now we check if this y added into this t is smaller than x. So if it's still smaller than x, this means that there's this many possible moves for this current position, and this letter at this position I should be also smaller than the string that we're looking for. So we should add this into our total number of possible moves. So otherwise, we will stop this small loop inside here. So this will give us the letter for the current position I. So at the end, we will just have to print out the temporary string, because every time we see something that is greater than the total number of count, so if this added to the total number of count is greater than or equal to the x that we're looking for, we should just stop this loop, because that means this current character will give us the nearest answer to this x that we're looking for. So this also goes through all of the characters, and then finally we just have to print out this temporary string. So basically the opposite of what we did here in the beginning, but here we're both using this count possible moves function. So finally we'll be able to get the total number of strings that are before this current string.